welcome. We are going to be talking this afternoon about the way forward with forecasting accuracy. The title has changed slightly from the title that was actually in the initial handout. Sorry, just shut that down.
Sorry, that's me.
I'm echoing. So the title has changed slightly from the title that we had originally in the outline for OR 62. And we've now got it as the way forward with forecasting accuracy, perspectives from statistics and machine learning. So we're looking at the use of statistics and machine learning. They've been much informed by competitions over the years, as we found that combinations often work very well. We have people with us today who can help us discuss all aspects of this, who have expertise from using statistics, but also have used machine learning. Some have used both, some are more particularly expert in those different areas. But we then also have someone who particularly looks at using these things in combination. And this is where a lot of effort has been put recently. So hopefully we have most people with us now, and we will move on to our housekeeping slides. So we recommend that people use on their screen, and this is only for those of you who are actually using your computer as opposed to using your phone. You can move the speaker into the top right-hand corner here where the red square is, and that will make it easier for you to see the slides as we go through. Please use the chat function to send us messages rather than raising your hand. And if you have questions, please put them in the Q&A. If you don't put them in the Q&A, we won't pick them up as a question that needs to be answered at the end. So if you can put them in the Q&A, please. We will include some time from Q&As at the end of the presentation. This is a panel discussion, so obviously we will be discussing certain questions before we ask questions from the floor. You can upvote questions to weight them. It would be great if you would do that, and then we know what's most popular. And during this presentation, sorry, there's not going to be any polls today. A video will be available after the session, after the conference, and we'll communicate all these dates. If we have any questions left over, we will also be putting them out to our panel afterwards. So let's get started on the actual presentation. So the agenda. We have three speakers who have expertise across machine learning and statistics and combination. Our first speaker is going to be Nicholas Correns, and I will hand over to him without any further ado. Thank you.
Thank you, Christina. So just a bit background on who I am and so on. I'm currently a professor in predictive analytics at a university in Sweden. And I think my contribution to the talk is mainly because I have many different backgrounds. So I started in much more qualitative research in strategic management, and eventually I edged my way through to econometrics and artificial intelligence. So hopefully I'll bring a bit this dimension here. As for research interests, I won't take too much time on that. I would just say I'm mainly interested into tackling uncertainty in the predictions, but also in the model specification itself. And in trying to address that, I have looked at various different topics. One of the ones I'm looking more recently is hierarchical forecasting. Perhaps people who follow a bit my research know that already quite a bit. So I'll jump directly to the points I would like to make, just to save ourselves a bit of time and leave more for the discussion. So if we just go to the next slide. Yeah. So we arrange the whole talk so that each one of us gives a brief on how we see the past, the present, and the future of each particular aspect of the discussion we're talking about. And I pick up the statistical approach. My panelists argue that I have the more statistical understanding. I still underline my strategic management background, so I will avoid putting that title to me. But nonetheless, I've done quite a bit of research on the area. So I think what we can say about the forecasting field is that from one hand, it's a relatively young field. I mean, it exists for about 50 years or so, I think, all in all. And it has multiple facets. From one hand, you have the traditional econometrics and statistics, Back to Box and Jenkins, for example. Then you have a lot of influence over the years from the more practical approach and the business forecasters. And exponential smoothing starts exactly as such, and eventually has become a rather mature family of models, for example. Then you have, of course, over the years, different attempts from machine learners and AI approaches to conquer the field. And I say multiple attempts because, we've lost count in how many revolutions in AI we have seen so far, but hopefully this one is to stay. But clearly there have been previous attempts in the past that, from one hand, influenced the field, from the other hand, did not leave a lasting mark as we hope it will happen now. And a fourth element that is becoming increasingly more relevant, and that's very nice to see, is the behavioral organizational aspects of the forecasting field. So if you put all of this together, that gives us a bit what makes up this field as a total. I would say that the big move that has happened in trying to, on one hand, embed all these ideas together, but also provide a tool that is scientific, is essentially an approach to sort of move from a method to a model. Instead of having just an ad hoc forecast function or a set of forecasts that I get somehow, we're trying, at least in the econometric statistical point of view, to come up with models that give us a good understanding of what is the uncertainty of our predictions, give us understanding of how we go about and actually specify and select the different versions and forms of these models, and importantly, quantify the uncertainty of the predictions through the prediction intervals or other approaches we can have for that. So I would argue that all the years in the past have more or less helped us to, let's say, put all these different disciplines together in a common framework from one hand, and move from the infancy of having just forecasting approaches to having forecasting models currently. Now, looking at the present then, I would argue that the biggest understanding we have is that the uncertainty is not just in our data. This follows quite nicely actually from our plenary from Christinas, that the point there was actually, how do we make sure that when we identify our models, we tackle the uncertainty we have in the specification of the model itself? And that has been one of the key questions we have seen over the last years in forecasting. As we have more and more data, as we have more and more computational power, we're trying to somehow balance these two aspects of the statistical elegance with the computational brute force to come up with approaches that give us a good specification that is robust against the uncertainty, both from the data and also on the lack of understanding of our forecasting problem, like what is the data generating process, as we would say from a statistical point of view. As we're doing it, the size of the problem is changing. The number of time series is ever increasing. Retailers now can have millions of time series to forecast. The number of predictors we consider can also become substantially higher. Looking at the work that has been done, for instance, on leading indicators, you can easily reach 100,000 of predictors quite easily. There is diversity in modeling objectives. Accuracy is no longer the king. We think about, for instance, the predicted distribution. We think about making your life easier in terms of decision making and so on. And I would argue again, as I said before, my research in hierarchies, I would say that also brings another aspect of how do we make forecasts that are actually useful for the decision making in the organization itself. So that quickly gets us into the future, where essentially we are at a point where now we're moving fast towards beyond just having a point forecast. We're looking either at now predicted distributions or even higher dimensional objects, if I can call them like that, that they also marry together things like what is your decision making, what is the objective, or even multiple objectives from different aspects of the organization. And this can be reflected in things like diverse loss functions. We're no longer just looking at mean squared errors. And this is in some sense heavily influenced by more machine learning engineering approach as well, which in many ways, to me, it seems to be the future. How do we actually put the traditional forecasting approaches, this model-based thinking, together with the machine learning so that we can address these modern emerging challenges?
So thank you very much, Nikos. That's a really interesting introduction to where we're going and where we've been. I now move on to Sven Krohn, who's going to give us the machine learning perspective. Thank you, Sven.
Thanks, Christina. Yes, I have a few more perspectives I could give, but in the interest of time, I'll try to keep it short. I'm working as a lecturer at management science. I think these days it's probably rebranded to business analytics at Lancaster University. I'm really pleased to see some former colleagues here. I'm also I'm also heavily engaged in implementing forecasting research in practice. I mean, Lancaster has a very strong tradition on that, and we have traditionally done that from master students on to engaging as a forecasting research center or a center for marketing analytics. But a few years ago, we actually went one step further. I spun off a small company, and we have now been implementing AI and ML methods in forecasting with various companies. So I try to provide that sort of insight into that. I've also been heavily involved in the IEEE, so I can share a little bit of the of the viewpoint that large engineering associations might have. And the final point, just a small one, we have to, all things aside, be aware that this is we're talking about a niche, right? If 84 publications and 2,500 public citations basically rank you high internationally, it just means it's a tiny field. AI and ML in forecasting, right? Unfortunately, so we'll have to work on that. But if we can move on, I want to portray my perspective a little bit with regard to the first, the kind of neural network history that I've had in industry. And Christina, can you just move on one slide further, please? I mean, ever since building my first neural network in 1998 for my PhD, I've basically been hooked on this. I found it a fascinating area, and I have seen the past, which has really seen a myriad of algorithms and also software packages to support them since the early days. I mean, we shouldn't forget the very first forecasting paper with neural networks, which is generally termed AI these days, although it's just a sub-symbolic part, was by Paul Werbos, who basically invented the backpropagation algorithm in his Harvard PhD thesis 1974. As all of you that have a PhD know, hardly anybody reads PhD theses these days, and it wasn't different at the time. But he actually looked at ordered derivatives. He was looking at econometric forecasting and how we can build nonlinear functions. And since then, we've seen 8,000-9,000 publications, and more recently, a massive amount of interest in deep networks. What we shouldn't forget in the success of deep networks, they are in very different areas. Although in forecasting, roughly 15% of all publications are in deep nets in the last 2 or 3 years, I've not really seen any convincing applications in real life. One of the things, just a side note, is that I think for the success of AI/ML in other disciplines, we shouldn't forget that they have been incredibly active building very large data sets like ImageNet in order to build training examples. And I think that is one of the things where certainly some of the competitions have come into play, the ones that were constrained to a particular research domain, such as the latest M5 competition. Other than that, until then, the forecasting community has been rather obsessed with the M3 data set. I'm guilty in part of that as well, having conducted the NN3 competition with Kostas Nikolopoulos many years back, but like a subset of the M3 data. But ever since then, I have to say, there was a certain resistance from the forecasting community to embrace AI and ML methods. I don't know if some of you remember heated debates with the likes of Scott Armstrong or the papers by Chris Chatfield. I mean, rightfully so. I think that is certainly the past. And now we see an even bigger hype. I see academic research in AI and artificial intelligence, machine learning is accelerating, possibly, not really driven by the challenges that actually are being posed to forecasting, which I see in possibly in practice, right? Higher data frequencies. I don't see a lot of industry case studies and proof of concepts from industry that get disseminated that actually are very successful. So I do see that a widening gap between the academic hype and the Gartner-fueled hype from the consultancy companies and the actual implementations. And of course, that is something that hopefully our impact cases can deliver in part. But I feel the gap widening, and I feel also that some of the software players and large consultancies, Amazon and others, are taking over a much more prominent role in driving research agendas forward and making algorithms prominent and putting them on the map that basically require enormous amounts of compute power, but often fail to outperform the naive method. And there's few implementations that really are successful. So, but Seema's already pointed that out today, right? There's very limited understanding of some of these algorithms today beyond accuracy, right? He talked about interpretability or transparency. If we looked at efficiency, robustness, other things, then I think there's lots of things to be explored, not all from an OR perspective potentially, but although I think the OR group is particularly well suited to have this balanced view of, how does it help practice or practical problems, because it's not just accuracy that drives things. And for the future, I'm amiss. I do think we have fortunately stopped looking at monthly data sets of the M3 and so forth, trying to outperform with very complex algorithms, univariate time series problems with 36 or up to 60 data points, right? There's very little to be gained in that. So I'm pleased to see that some of the recent data sets are more challenging and possibly benefit other things, although I think there's a small sample selection bias in the participants to these competitions these days. But that's it. And I'm also interested in seeing AI ML seen in a more wider context. If you think about the whole demand planning process, if you think about supporting the managerial decisions behind the essence of forecasting, then we're normally looking at demand planning or other things. But there are various steps such as history correction where you can use AI or ML methods. We can look at providing human-computer interaction, so visualizing, explaining particular aspects of forecasting, maybe even reviewing forecasting adjustments. And I think looking at AI ML just as an algorithm might be too narrow-minded, and we have to think about a bit broader. But that's it. I mean, that's my viewpoint on how I'm going to come at the panel today. Hopefully that
That's lovely, Sven.
That could contrast Nikos a bit.
Thank you very much. I think you're going to be complimentary, I'm sorry. So on that note, talking about the use in different places and combining machine learning and statistics, we move on to Devon Barrow, who's going to talk about combinations.
Okay, thank you, Christina, and thanks to the OR Society for giving us this opportunity today. And thanks, Nikos and Sven, for joining me on the panel. I'm an associate professor at the University of Birmingham, very much in operations management. But as we know, research really focuses on forecasting. Like Nikos, I've had a background in business. I was once upon a time a chartered accountant, believe it or not, but very much my academic training is in computer science and statistics. And I would say maybe 10 to 12 years ago, I began this journey of doing my PhD and looking at the topic of forecast combination and selection. And ever since then, I continue my research in that area, but expanding into applied areas of inventory and call center management. But also oftentimes you get pulled by the requirements of what is needed out there, and recently looking at some projects in terms of the wider subject of data science and small and family-owned business. I've been looking into Jamaica, where my wife is from, and also looking into some projects on forecasting and education. So that's just a little bit about me, but I want today focus on forecast combinations, as we say, past, present, and future. And again, this will take me back to when I started my PhD, because that's really where the root of my research has been. And it's the past, but the question still remains to combine or not to combine. And ever since the work of Granger, when he phrased the problem of a combination of forecasts, and the work that's been done since then in terms of forecast encompassing, do we need to forecast? Should we just select? The past was really about developing the field, and providing a platform that we could start to both theoretically and empirically argue for whether we need forecast combination or not. I think if we look to today, the evidence is a bit overwhelming. Even the recent M4 competition saw that nearly all of the top ranked methods of the competitions involve some sort of combination, whether involving only statistical approaches, as Nikos has summarized, or machine learning AI approaches, as Sven has alluded to. There is also a question, and when we look to the present, beyond accuracy, and I know that the talk is entitled accuracy, but I'm sure many of our panel and audience will agree that looking beyond accuracy to complete error distributions, to the decisions we're taking, to in and out of sample consistency, that's also what is quite interesting at present. I want to focus on these 3 points: sources of uncertainty, diversity, and pooling, because I think that's where a lot of the current research around combination is focused. Why do we combine? We oftentimes, or at least I think about combination because there is some sort of uncertainty, whether it's due to the model specification, whether it's due to small sample data. There is something that we're uncertain about that, and it goes back to Chatfield's work, that we're trying to mitigate against. And a lot of the work has gone away from just looking at, thank you, Christina, just looking at weight estimation. So how do we estimate the weights that will be used to combine these approaches, whether statistical or machine learning, to how do we generate the forecast that will eventually combine? Will we generate those forecasts based on looking at the temporal uncertainty, Will it be based on the data uncertainty in terms of using bootstrapping or temporal aggregation? And therefore, how will we create diversity among our forecasts? And Nikos and I have done some work on pooling as well. So can we select a smart subset of forecasts that we can then combine regardless of where these forecasts originate? In terms of the future, again, results of the M4 competition and a lot of work that's being doing now, there seems to suggest that there is something to be gained in combining machine learning and statistics. How that is to be done is probably where the focus is going to be. People like my colleague Photius Petropoulos and others, Robert Files and others are looking into human judgment and how we can combine human judgment, because at the end of the day, we have decision makers that are going to somehow adjust or do something about these forecasts. There's a hybrid approach, and funnily enough, this method by Smil actually was is the winner of the M4 competition, and that was an approach that in some way integrated exponential smoothing and recurrent neural networks. So I think that's going to be an interesting way. And linking back to the discussion this morning, you combine a bunch of forecasts. How do you interpret it? Is there a forecast that's dominant? How do you make sense of all of it? And I think linking back to how do we interpret it, is it suitable for decision making beyond forecasting accuracy, is probably something that we'll need to address as well. So those are my perspective in terms of the past, to combine or not. We've got the answer, combination works, and the future is about, where do we go in terms of machine learning and statistics, but also other things such as human judgment and making sense for decision making.
That's lovely. Thank you very much, Devon. So I'm going to stop sharing my screen now, and we're going to move over to a panel discussion. Everybody's covered to some extent the past, the present, and the future of forecasting, especially with regards to statistics and machine learning and bringing these approaches together. I think an interesting aspect of that is, so what's actually worked and what hasn't worked so well when it comes to combining these methods, or also when we've gone off just down the statistics path, or we've gone off just down the machine learning path, and we haven't thought about bringing them together. So who would like to go first on that one? Mistakes of the past.
Oh, probably I'm the oldest, so I probably have to talk about mistakes of the past. Is that right? What has worked, what hasn't worked? I think there are two hats, right? I think if you ask an academic, everything that we're currently looking at probably deserves some attention in order to be enhanced, to be questioned, to be second guessed, and to be reevaluated, reassessed. If you ask a practitioner, he would probably be already overwhelmed with the choice he has, and he would say pretty much everything seems to have worked. I mean, there's a massive gap between industry practice and academic research in forecasting. The most prevalent methods still are simple averages, followed by exponential smoothing if you take an average of industry. So I think if we look at industry, what has clearly worked and was very hard to outperform is exponential smoothing. Yeah, I don't know if I should talk about what hasn't worked, but if you think what maybe in the past, more taking a step back, what has worked well and what hasn't worked so well is, I think Devon has made a good point that combinations seem to have worked both on the forecasting side, traditionally coming from an OR and maybe statistically fueled backgrounds, and at the same time combinations are prevalent in machine learning, so computer science domains and data science as well. Having said that, looking at the past, there's hardly any cross-fertilization of people in the IEEE or in the computational intelligence world reading OR magazines and journals. Paul Werbos quite literally had a rant at one of the World Congresses on Computational Intelligence saying that if you don't know how to build an ARIMA model, how will you ever build a recurrent network? And people just said, what is an ARIMA model? So I think there was little cross dissemination of research interest and things that practically work between the engineering world, and at the same time back to the management or management science world, where IIR and infinite impulse response filters are basically reinventions of AR and MA and ARIMA models in engineering that have been used in practice for years. So what hasn't worked so well for me is this cross-fertilization across disciplines.
So would anybody else like to put in something there, Nikos?
Go on, Nikos.
I can jump in. I'll go more into picking up a bit on where Sven ended up, but I'll go a bit more on the specifics of what hasn't worked, perhaps. I think forecasting is, whether we like it or not, at the core of all decision making. If we're going to take a decision about the future, we need a forecast. however we get that forecast. And obviously, when academia is trying to help society in practice, people are trying to do forecasting one way or another. However, there are very good principles that have been developed in this community over the last 50 years or so. And often this is lost. When people from different disciplines, or sometimes even ourselves, we try to solve a problem, we do it very heuristically, and we sort of forget that this is also a field that is trying to become a science itself. So for instance, thinking about AI and ML, and I'll jump a bit to the recent of coronavirus, perhaps even this way addressing one of the Q&As. I was enjoying with my group looking at all the different contributions you could see daily, either in blogs, in LinkedIn, or even in academic papers being reviewed 1 or 2 days only, or even less than that. And many of them were like, let's get some new data, let's apply something, let's get something out of it. Well, hold on, what decision are you supporting? Have you benchmarked your approach against something that's much simpler, much more transparent, interpretable, and only requires click of a button to get an answer, like a very simple exponential smoothing forecast? So there has always been a love for more complex techniques. And obviously, I'm guilty of that. I'm an academic. I publish methods and methodology papers. So I try to make complex stuff to make, my papers getting published. But after a point, we have also to take back a step and ask ourselves, AI and ML bring a lot of new things to the field. Advanced econometric methods are equally arcane, I would argue, and they also bring very good ideas. But are they actually done in a way that they help decision making? Are they actually solving the OR problem, or are we just advancing our modeling and our mathematical techniques?
Yeah, I mean, I'll jump in, and what I would say is what I've observed is quite often, the fact that there's a bit of a theme around competition in terms of when we first started thinking about having this session, and very much, sometimes you feel there is a competition between developing approaches within statistics and evaluating these empirically and theoretically and so on, and what goes on in machine learning. And this idea, as Sven mentioned, in terms of these fields developing in parallel, but to what extent is there integration between these fields occurring? A lot of the approaches, if I stick to combinations, bootstrapping, for example, had been done. So this is the work by Bremen, who developed random forests and using bagging, etc., for quite some time in classification. I was only recently that we started to apply bootstrapping. I think Cordero is the person who really started that first, and then there was work by Bergmeyer and Hyman and Petropoulos and so on, who started to apply bootstrapping to exponential smoothing. And similarly, there's been a lot of developments in terms of what can we bring from machine learning AI across the statistics, and vice versa. So I think in terms of what we know to work, we know that there are certain strengths in terms of statistical approaches and so on, and then there are certain strengths, for example, that machine learning brings. And I think that's brought out in the recent hybrid algorithm that I referred to earlier on, where we see, for example, exponential smoothing being used, and exponential smoothing algorithms being used to determine, okay, what are the basic components within this time series? Nikos has done some work on that in terms of input variable selection for neural networks and so on. So how do we in a very smart way select the inputs for neural networks, and using things from statistics in terms of partial autocorrelation functions and all these things, but then also giving that to the neural network, so working hand in hand with machine learning to then say, you go on and do the other stuff. So I think this idea of parallel development of the two areas, but the coming together, the cooperation rather than the competition, is probably something that is starting to emerge, centered and more focused around the decisions, as Nikos has put it.
So I'm going to answer this question in a minute, but I'd really like to keep on this theme of what's worked and what's been learnt for the moment. It seems to me that what you're saying is that in the past, these have been two quite distinct and separate fields, but what's happening now is they're really beginning to come together, and you're noticing more and more areas where different things are applicable. Would that be a fair assessment?
I'm not sure we're there yet. I'll probably hand over to maybe even Sven or so, because Sven is really in terms of what's happening in practice and in companies and so on. I'd like to think in research that is what is happening, but I'm not sure. Sven, what do you think? Maybe. I don't know.
Well, I think talking about industry adds a completely different dimension to this, right? But
Yeah.
if we just look at the academic fields, then I think there is limited engagement of in general between the engineering disciplines, electrical engineering, you know, in particularly the large multinational associations and the OR societies, and vice versa. Although there's often a discussion in each of the societies, I feel, about the ownership of that. What can we bring to the table, or what are we failing to bring to the table to do that? I mean, clearly nobody can rightfully claim owning deep learning, right? I mean, not even the Computational Intelligence Society said that, because most of the research was done in the ACM and not in the IEEE. And then there's this ownership. We organized an industry conference in San Jose, and there was multinational corporations that are using this, the likes of GE and Ford and Toyota presenting, and most of them presented machine learning, and all the presidents are sitting there saying, like, this is not computational intelligence, right? This doesn't belong to us. How can we use this? I think in the OR world, we have a very important contribution by understanding about the decision problems and how it's how it supports real world decision making in industry. But to be fair, engineers have the same viewpoint, right? So I would see it very complementary. I think it has something to do with journal policies and other things. But with regard to the view on industry versus academia, right, the gap has widened so much. I mean, it's we have to understand different levels of adoption of automatic analytical decision making. You have electricity companies or utility companies that actually have had to make analytical decisions fully automatically for many years, and they are very much further in the adoption than the majority of consumer packaged goods companies, retailers, and a variety of other companies. So, but the gap is widening, and I think we're just alienating a lot of practitioners with adding more algorithms to the choice that they have, although it's relevant. But I think the competitions there play an important role, and they can actually help. But any sort of discussion on would you like to have this algorithm combined with another algorithm, that is beyond the scope of anything I've ever seen in a software pitch, even in a multinational corporation, you know, driven in digitalization. I'd put it that way.
Sorry. So what about you, Nikos? Have you got anything to add to what we've learnt and how you see things moving forward?
I'd be surprisingly optimistic on this one. At least seeing the interaction of many of the companies I have worked with in the past few years, but also with various academics I talked to, there is a very prevalent OR spirit in the way we do research now, in forecasting at least. People are trying to solve problems that make a difference. And I see that this is being adopted in both sides of the spectrum. Yes, we're not exactly there yet. And, you know, again, myself being guilty of that sometimes, but I do see actually that this whole movement of open sourcing solutions and then software companies adopting many of the modern solutions, this speed of research to practice has increased a lot. That brings to the fore many new interesting data sets. M5 is a very good example of that. It is a retailer who came forward and said, here is my data, let the community deal with it. It's a fantastic initiative in that sense. But also researchers saying, okay, my usual toolbox is these 5 items, let's say, but this problem requires a 6th one. I have often enjoyed discussions where people tell me, coming from a very specific, let's say, point of view, oh, but you don't have enough data to solve this problem. Why do you bother? Well, companies have to solve this problem, so I have to solve this problem as well. Or from the other hand, you know, this looks too complex algorithm, nobody would use it. Well, hold on. It's not like you know most of the things in reality, how they work. You still use them quite comfortably. There is somewhere in the middle to have the discussion with the practice and the researchers and finding a common way forward. But I think this is becoming more and more frequent rather than the other way around. People are willing to go in the middle, and that's very nice.
So to carry this on, we have one question at the moment, which I will ask in a moment. More of them are beginning to come in, which is great. Do upvote them if you would like to see one answered more than another, please. So to just finish off this part of the talk, about where we're moving in the future, and a few of you have picked up on the connection between forecasting and OR. Personally, I see them as being very deeply connected. And as you say, Nikos, we're beginning to become more practical with our forecasting rather than just coming up with methods that are for greater accuracy, but do these methods actually work in practice? So how do you see us moving forward with forecasting, and in particular within the greater landscape of operations research and operational research?
I can start with that. I think perhaps here, since you're the person who's asking the question, I can refer slightly back to you and saying, your research area is actually testament to that. Sometimes, some years ago, we would say, okay, here is a purely econometric paper, or here's a purely machine learning paper. These papers are becoming more and more rare. There is always an organizational aspect to them, or at least an increasing organizational aspect to them. And even now, there's a behavioral aspect to them. Some of the more interesting discussions I've heard recently about AI is how to actually embed expert information within the system so that it can address the usual questions we face in a way that it's going to make the human out of the loop. How do we keep the human in the loop? And this kind of discussion has also, in some sense, moved also to the statistical way of thinking. In many ways, very well echoed in the plenary beforehand. Interpretability, no matter how you're going to define it, is becoming a key element. People say AI is not explainable. A regression with 20 variables is not explainable either. So in that way, I personally see this idea of having the organizational aspects, what defines our decisions, and also the behavioral aspects becoming a key element in both the AI and the statistics as the anchor that brings them also together.
Thank you. Yes, that is quite close to my heart. As you say, the behavioural aspects are important. Now, how do we deal with things like that, though, when we're talking about sort of complex AI algorithms? I mean, that's Sven, that's your area, but you do a lot of work with industry, actually putting this stuff in place. So how do you deal with that?
Oh God, that's a very tough question to answer. I mean, one thing I can say is, first of all, 70% exponential smoothing, 20% causal regression models, and then 10% of machine learning to add on top, because you don't want to complete. To be fair, I mean, it's never a single algorithm class or family that can dominate the complete complexity of a real world data set, right? So that's why I think this whole idea of developing algorithms is different, and proving them on large scale data sets is probably not the realistic one. You have to look at methodology and how to select between these algorithms, right? Is it a short time series, a long, noisy one? Does it have outliers, zeros in it? I think things that are intuitive. So one way I would hope that research and industry can play together in the future is that at the moment we have established this format of competitions and large-scale empirical evaluation as the only way to derive knowledge, right? Real insight and what works, what doesn't work. And engineers don't do that, right? And in engineering and computer science, it's absolutely sufficient to to show a theoretical innovation, justify it, and then show its properties under one experimental development. And they're much faster in publishing things, and arguably I think at the moment they are leading the way in developing algorithms that actually solve industrial problems. So while I very much in line and like large-scale empirical evaluations, a lot of feedback from reviewers these days is you're only evaluating this on 10,000 times, you have to do it on 50,000, you have to create prediction intervals and so forth. That's not relevant to that. And so I do hope that we balance two things, right? It's not just all empirical evaluation, it's not just empirical accuracy, it's also the theoretical merit. I like representing model structure and developing this further. If you think about deep learning, basically those were people from computer vision or language that understood the properties of the model that were required and embedded them into a structure for a neural network. Right? They introduced convolutions, they introduced long short-term memory, exactly tailored to the specifics of the data set, but they didn't have to empirically prove this on a gazillion data points that it actually works. That's a different problem. But so I hope we can move away a little bit more to the intellectual merit of some of the inventions that are coming outside of this domain. And I think merging optimization with machine learning, as Betsimas has shown this morning, is a brilliant example of that.
So that
although
speaks
he also proved everything, so to be fair, right? I mean,
well, yeah, he would. I was going to say, Devon, that really speaks to combinations and how you do combinations and the cross-disciplinary aspect of this.
Yeah, definitely. I mean, what I was thinking about was this idea of being guided by decisions. I think COVID is a good example of that. I think we've seen, the situation that happened with the algorithm and student grades, and how that panned out. So I think as Nikos has mentioned as well, I think forecasting, machine learning, that we need to be guided more by the decisions. I think Sven has a point in terms of accelerating and recognizing quickly what works. But there's also, I think, a point in the discipline and the science of why things work. And I think, as Sven has suggested, both are important, and the balance is important. And in a way, if thinking of competition, stats does not want to get left behind. I think there is, in a lot of my research that I do, there's also the idea of diminishing returns. And Sven made the point, 70% exponential smoothing and so on. So at what point do you continue to look further and to further optimize and integrate an algorithm, a machine learning algorithm? At what point do you stop getting into the details and focus on what are the added benefits of this solution to the particular problem that we were derived? Because at the end of the day, these decisions, as we've seen with COVID, are going to impact people. And Nikos has made a point around behavior and other things like that. And it goes back to my point in my summary that human judgment and these types of things are coming into play a bit more. So I think, unfortunately, on a slightly pessimistic note, I think we'll probably see the future will probably hold a bit more of, stats doing their thing, sort of machine learning, AI just going at a top speed, because very much, there it's about solutions oriented, and there's a lot of data that's being worked with. And I think the merger is going to happen slowly. I think actually the people who are creating the best solutions, the best methodologies, are those who already recognize that bringing these together, combining them in terms of a hybrid or some other approach is the way to go. And I think those researchers who recognize that, those persons in practice who recognize that, are the ones who are going to be sort of leading the way. Whether they call themselves machine learners, or whether they call themselves statisticians or econometricians, those that recognize that connection are the ones that are going to be creating very interesting research and application in the future.
Perhaps they should just call themselves operational researchers.
Exactly.
It allows you to be nice and multidisciplinary then, doesn't it? Yeah. So we've got a few good questions, and we've got one here that's been upvoted a lot by somebody who you will all recognise. Robert Fields has asked, what does the panel see as the prime barriers to adopting more advanced methods into organisations?
I think if Robert is asking a question, he should also pose his answer as well. but beyond that,
answer for him if you like.
I was about to say, I wish Robert was here to answer that. Yeah.
But I think beyond that, I think, as I said in my previous answer, I see the future a bit optimistically. Companies are realizing now that they actually need these advanced techniques. There are problems that we can solve now that a few years ago they could be science fiction. And all these are based on techniques that are well beyond what we would think as introductory forecasting. So from one hand, people understanding that these are problems that you can actually ask how to solve now, that's one thing. That takes educated people to be in companies, to have also the time to invest either in resources, in teams, or however they want to do it, to ask the right questions and contact the right people. But I also put here a bit the weight to the universities. It is important for the universities to let their staff, their academics, their PhDs, their master students, their undergraduate students, to have the time to actually do this thinking and this interaction. I'm very fortunate in my academic career so far to work closely with industry, and that has led me to very interesting questions. And that leads to more companies then getting in touch with me and so on and so on. But I've been very fortunate because I had the time to do that. Academia now is international, and if you wish, this Zoom meeting sort of underlines that. I could very well be in whichever country, which I'm not in the UK right now, and working in different conditions with different resources. If we think about the UK academia or the global academia, how we're going to go forward, then universities have to put these resources in place where we can interact with communities, with society, and we can help to better it, rather than just do whatever we're usually doing in our ivory towers, if you wish, or in our semi-lit offices that we enjoy as programmers, operational researchers, or however you want to put it.
So I take from that, it's not all about the ref.
No, absolutely not. It's about getting the interesting questions and working on them.
And if you've ever written up an impact study, you'll know that it's not all about that either. No, reaching out to companies and actually spreading the love of what we can do and what we could give them, which they don't know about.
Maybe I can add one small thing. I often get this very interesting feedback from students about YouTube channels from ex-academics who left academia, and now they're taking their YouTube videos and explaining very complex approaches with very good graphics and visualizations and so on. So the basic education in universities, I mean, that's a question that I don't know how to answer personally, but my take would be the basic education is a thing of the past in 10 years or so. But the idea of actually having the time to think through very difficult problems, structure them, address them, and help people go along, that's still in our mission. Education of that level, not education of teaching people how to do the very basics of linear algebra, perhaps.
Sven, do you have anything to add?
Yeah, well, going back to to Robert's question about the prime barriers to adoption, I don't really see university as the prime barrier to adopting more advanced methods. Whatever important role in society and research I allocate to the university, I think coming from my industry view, I think it's also not HR. It's not the perceived gap in talent or resources, right? Even if every single multinational company had 10,000 data scientists, you would just be thrown back in the 1960s, where everybody's developing their own code to solve things for problems. I do believe that that we have standardized decision problems that are prevalent in industry, and then they can be solved with advanced algorithms. By the way, advanced algorithms, I would include things such as intermittent demand forecasting with optimized parameters for inventory, or hierarchical forecasting. It could be very statistical, going back to the simple algorithm perspective of the special issue in the Journal of Business Research that Robert also contributed to. But I think the real obstacles to adoption are elsewhere. We have an incredible lack of innovation in systems, and responsible for the lack of innovation systems is not the interplay between universities and software companies. It is basically just software companies are gatekeepers to innovation, and they don't innovate well. Many of the large-scale ones have not innovated well, and they're basically in liaison with some of the largest consultancy companies, selling things that sell, but not solving problems well. And I think that is a real disconnect. I'm not sure if open source will be the solution to that, so that you can actually crowdsource and leapfrog light years of innovation. I see big players, OMP and others, all having roadmaps that probably are, SAP APO, that look to say, and this is where my knowledge stops, and from then, R will do the trick. Let others find the solution to this. But if you think about the adoption to innovation in companies in forecasting, I do think that software companies have a responsibility also to share innovation. And the most prevalent software system or forecasting system at the moment in the market is SAP APO. It has shown an incredible and astounding lack of adopting anything that research has published any time since 1956. Right? I think that's incredible. And if you're looking at 50% adoption, there are others that are noteworthy, right, that have driven research agendas forwards. But I do believe the biggest challenges are convincing software companies that different software designs are important, and you also need to curate what works and what doesn't work. It's not helping looking at a gazillion frameworks in R and then trying to pick the best one, the ones that are actually working. But I do see it there. And then it comes to the practical issue that these inferior systems have hindered the collection of meaningful data outside of retailing and electricity. So I think that's the next obstacle.
Yeah. And as Nikos pointed out, there's also helping people to understand how to use these things. So the software companies tend to override any of that learning, don't they? And then they say that they're teaching you everything, but actually there's probably quite a lot of underlying knowledge that would help. Devon, do you have anything to add to that?
Yeah, I mean, I do think education is quite important. In my my limited, young, and humble experience, you know, a lot of times when you try to make headways into these companies, there are usually some individuals there, just as much as software vendors are the gatekeepers. For many of these organizations, they're individuals. I've just been dealing with a company recently and talking to two specific individuals. And these two individuals will determine the rate at which our sort of interaction occurs and so on. And it just happens that one of them is an alumni from the University of Birmingham. So in terms of the university part of it and sending people out there into companies and so on who are aware of what is available, a lot of times you go into companies and they don't even know, much as to be able to choose. You get someone who is doing forecasting, and like much of us, I'm sure we'd appreciate, you ask them what their background is. They're not data scientists. They did geography and they did something else, and they did some demand planning training, and now they're a forecaster. So I think education in terms of influencing companies, but also, as Sven is saying, influencing those who are into software is important. But of course, I think what Sven is trying to say is that that's a bigger game. And I think that game is also related to, at the end of the day, the vendor is going to sell forecasting. They're going to sell a solution to this company. And I recently supervised a PhD dissertation, so a master's dissertation on technology acceptance model. And what's going to impact whether a company chooses a solution? It's going to, what does it cost us? You know, what is the ease of using that solution? So, you know, all of this is still sort of thinking in my mind, but there is something to be done around that area in terms of, well, why are organizations, what are the barriers? Why are they not accepting us? Well, let's look at some existing models that say, well, maybe it's too expensive. Well, maybe it's just diminishing returns. Well, maybe we just don't believe you. Well, maybe it's not easy to use. We don't have the capacity. We don't have 10 data scientists and stuff like that. So I think it's about cost and ease of use. It's about educating people so that the right people are in the organizations to affect change. And it's also about understanding that game, that system that Sven has described, which is about how software, and Sven knows a lot more about that, but how software vendors work with companies and how quick or easy or slow they are to change their systems and other things like that.
Okay, so we have just a few minutes left. We're at 10:02 now. So before we wrap up, I've got another couple of questions here. Now, one that was asked first, it hasn't been upvoted as much, but it was asked first, was about the role of machine learning in forecasting in the COVID-19 crisis. Do any of you have any experience of trying to use forecasting and any comparison perhaps with the epidemiological models? No?
We don't. I have we do have the pleasure of actually being live with a number of large-scale industry installations in forecasting, from Hapag-Lloyd, a very large container shipping company, to AB InBev, a very large beer manufacturer in Europe, pharmaceutical, medical product, medical device producers, and so forth. And all of them ran into COVID because they're all in production. And the role in ML-based forecasting is just as the role in any advanced statistical methods that basically are looking ahead at a major disruption where you don't know, are your sales massively going to skyrocket up because you're selling toilet paper, or is it going to drop into nothingness because the automotive industry decided to close down completely and you don't need adhesives anymore. So it is as versatile as everything. And basically, there is a lot of brilliant research. David Hendry and team in Oxford are looking at this, you know, looking at major disruptions, how to forecast. My best pragmatic recommendation was to switch our systems off. Right, but you can go to simple tools like the naive, which in essence boils down to that if you don't know where you're coming out, then you probably are not. It's probably not helpful to use a model that's been trained on 9 years of container shipment data that has never seen a single disruption. And even if you do so, how much would you need to oversample something like the Argentinian peso crisis to understand the Argentinian crisis in shipping wine out during the COVID crisis? So my best recommendation is, or was at the time, is that, you know, statistical forecasting is not the end of this, but in the complex demand planning process, you hopefully have smart demand planners, and they are then able to anticipate that. In order for them to make meaningful adjustments, you have to use simple methods that they can comprehend, like taking an average of the last 4 weeks of the running month, and then making meaningful adjustments. But we have been remarkably unsuccessful predicting COVID, but that's not surprising. But we did get some calls saying, like, why didn't you forecast this? And at the same time, you know, forecasting the upswing that we didn't do well, but then nobody in the company even know where that upswing is going to end up. So I don't have a solution to that. Having seen an outlier and having seen an anomaly, I think we can use ways in which we can robustify algorithms against it. We can identify early on that algorithms are leaving their realm of knowledge, right? Those are important things. Anomaly detection, building a second model around the first model to check for errors, residual, systematic over or under forecasting. But yes, unfortunately, we've certainly not been successful in automating that.
I mean, just to add to that, I recently hosted actually people from David Hendry's group, so Jürgen Dornick and Jennifer Castle, and so they were talking to us in the UKIF chapter about the work they've been doing, and in terms of actually using simple sort of linear trend models to outperform epidemiological models. That was part of some of their findings, but that was really to track sort of the exponential growth in terms of COVID infections and these types of things. On the panel, we also had a guy, Trevor Sidri, so he's the lead data scientist in terms of the strategic division at Tesco. And basically what he said was that it was scenario planning. So he said, you know, a lot of what Sven said about just looking at time series and looking at movements and stuff like that. But he said, at least strategically, I think Sven is talking about production operations, but at least strategically, he said what they were doing was sort of running a lot of scenarios and trying to plan against that. So in terms of, we've spoken about a lot of things, but sometimes when you listen to business as well, you also start to realize that maybe there are things that are missing or they have a different emphasis. So for me, that was one takeaway from that session in terms of the COVID response, at least from the Tesco perspective.
We have one final question that we can squeeze in there that I'll put to Nikos since he hasn't spoken for a while. In what types of application are AI/ML forecasting techniques limited and not appropriate for real-world decision making? So when are they not appropriate?
I don't think it's easy to say a general class of problems that you would find this to not work. Traditionally, we would say when the data is limited, it's not so easy to learn from the data. But you know, if you look at the literature, there are actually papers that suggest here is a trick so you can overcome this or other limitations. But to me, I think it's a matter of, and perhaps this is something we didn't make enough stress in this panel. It's a matter of not being dogmatic about either being an AI person or an ML person or whatever is the most fashionable thing next year. I follow the discussions with practitioners or when I discuss with industry, and everybody says, yeah, but have you tried AI on this? Or why don't we try an AI? Well, I mean, in some cases it will be better, in some cases it will be worse. But as long as we match the kind of predictive model we're doing with the needs of the industry or the company we're trying to advise, or let's say if it's a state organization thinking about COVID and so on, then I think it could be very applicable. It's just a matter of not being blindly about it and just trying to force a neural network when even it's not needed.
Maybe I can add just one short thing to that, because it relates to what I said. There's very few industry cases. There are very few industry cases published at the moment because very few industries actually stick their neck out and say, we tried this, this way, that way, and another, and it just doesn't work, right? But you don't really publish failed experiments. You don't release failed proof of concepts from industry into practice. And the same thing, when I think it's more interesting in the competitions to look at the long tail of things that didn't work, which is one of the reasons I don't particularly like Kaggle results, because they focus on the winners, which is natural. But we have to learn about things that don't work. There are very few journals on negative results, and hardly anybody reads them because it's depressing to see everything that doesn't work. But I think I very much like the question, the way it was phrased, not about, where do you think it works? Because the marketing hype is, it works everywhere, potentially, just try it. I think there's some clear-cut cases where it's very hard to do that. I'm pretty certain that on monthly industry data, consumer goods, pharmaceuticals, and so forth, without any additional knowledge, like out of stocks, budget numbers, other things, exogenous variables, additional insight you have in the organization, it's very, very hard to outperform that with the normal level of data that's held in these systems, which is still 36 months. So you basically have 3 Christmases to predict something. How much do you expect from a nonlinear algorithm to find nonlinearity in 3 data points? But I like the phrase, if we can identify negative cases where it clearly doesn't work well, I think that would be important. And maybe that's something where we have to disseminate. That's where universities come in play, right? Because we don't lose our face if we publish something that doesn't work, although we rarely do that.
Yeah, it would be nice if we did that a bit more, looking at both what works and what doesn't work and balancing that and learning from both. Yeah. So thank you very much to all our panelists today. I'm going to have to wrap up now. We're in the final minute. I'm sorry we didn't get to the last question. But thank you very much to all our speakers today. Nicholas Krantz, Sven Krohn, and Devon Barrow. Thank you very much.
Thank you.
Thank you.
Pleasure.
Have a great conference. Bye.
Thank you.